It's my pleasure to introduce today's keynote speaker, Alan Lee, Chief Technology Officer of Analog Devices Incorporated.
It's great to be back here at DAC. You know, our technological world continues to change at an accelerating rate, and design from chips to systems has never been more important. AI has emerged as a dominant force over the last 2 decades, rising in its current form from the confluence of advanced algorithms, immense data sets, and huge computation. As a mathematician, all 3 of these factors interest me, and I've had the pleasure and honor to work on all 3 during my career. So, a little bit of history, and speaking of mathematicians named Alan, next year will mark the 75th anniversary of the Turing test for intelligent behavior of machines. Moving forward from that, in 1956, the Dartmouth Summer Research Project on Artificial Intelligence, with luminaries such as Minsky and Shannon, kicked off AI as a true field of study. Then, after a bit of an AI winter, we had a rebirth of AI algorithms, with workers such as Jan LeCun and others at AT&T Labs on handwriting recognition. Personally, I remember the NSF Institute for Pure and Applied Mathematics hosting a summer program in 2012 that brought together Jan LeCun, Andrew Ng, and Jeff Hinnon to speak about the latest in neural networks, graphical models, and deep learning. 2017, of course, saw the release of the paper, Attention is All You Need, and Transformers. And it's hard to believe this, but ChatGPT was just released in November 2022, only a year and a half ago. And think of how much has changed since then. Modern AI systems, particularly deep learning models, have become incredibly powerful, capable of processing and analyzing enormous data sets, often with terabytes or petabytes of data, to identify patterns, make predictions, and improve application performance. However, this capability comes at a cost. State-of-the-art models like GPT-4 require vast power and compute resources and the ability to move tremendous quantities of data. Large AI systems require extensive training on immense data sets before they become operational, or more accurately, valuable. Central AI applications are often housed as compute data centers with thousands of GPUs or similar processors, delivering the extensive computation necessary to train large language models and foundation models. In many cases, the data movement, both from storage and internal to the compute clusters themselves, adds substantially to these power requirements. For example, it took 50 gigawatt hours of electricity just to train ChatGPT-4. For a little perspective, that much energy could power more than 4,600 US homes for an entire year. And that was just to train ChatGPT. Now, in terms of daily operation, ChatGPT manages millions of interactions and consumes more than 500,000 kilowatts of electricity every day. That's about the daily usage of all the households in Oakland and Berkeley combined. Given that each interaction can involve complex queries and responses, the data throughput is immense. All this data needs to be transported rapidly, efficiently, securely, and successfully. My next few slides will discuss applications of AI in healthcare, manufacturing, and energy. We have a technically gifted audience here at DAC, so as I describe some of these use cases in high-level terms, think of how you might design solutions from chips to systems. Starting with healthcare, AI is revolutionizing medical imaging and diagnostics. Advanced algorithms can analyze medical images with remarkable accuracy, assisting clinicians in early disease detection and treatment planning. AI-driven models are also accelerating the development of biological therapeutics, identifying potential drug candidates by simulating and analyzing their interactions at a molecular level, significantly speeding up the drug discovery process. In manufacturing, AI is enhancing everything from predictive maintenance to quality control to supply chain optimization. Sensors and AI algorithms are monitoring equipment health, predicting failures before they occur, and reducing downtime and maintenance costs. AI-driven quality control systems are enabling anomaly and defect detection in real time, allowing rapid adjustment and yield improvement. AI is also optimizing supply chain operations by improving demand forecasts, inventory management, improving overall efficiency, and, most importantly, reducing costs. In energy, AI plays a crucial role by optimizing and creating greater resiliency in smart grids and improving the utility and reliability of renewable energy. AI algorithms manage energy distribution in real time, balancing supply and demand, and enable rapid fault detection and response to minimize energy losses. AI is enhancing the efficiency of solar and wind power generation by predicting weather patterns and optimizing the operation of connected energy storage systems. Now, when thinking of the previous AI use cases, I'm guilty here as well, I bet many of you thought of large-scale applications of AI, such as large language models, LLMs, or foundation models. However, there is an even larger world of AI out there to be explored. Now, please pardon my middle school 8th grade earth science analogy, but this world or ball model provides a reasonable way to look at different types of AI solutions, present and future. In the center, we have the core, where the massive scale deployed AI systems live. At the crust, we have the true edge for sensors, wearables, and ultra-low power applications. And in between, we have the mantle, which consists of what you might call medium-sized AI. I view this as a ball because it emphasizes that the volume of the solution grows more rapidly the farther one gets from the core. Obviously, these areas are constantly changing and not as distinct as illustrated. In fact, an even more important consideration for this group is their interdependence. Today, most of our preconceptions about AI as huge models is justified. About 95% of AI workloads are now centralized in data centers. But as soon as 2028, it has been predicted that fully 50% of AI work could occur at the edge. The positive impact of placing the power of AI at the point of data acquisition and action will drive this integration. Just as computing migrated from centralized mainframes to PCs to mobile devices, AI will similarly evolve. The next frontier for AI lies at the edge. However, the path to getting there is anything but straightforward and simple. As designers, we need to think of design for AI, design with AI, and soon, even design by AI. Bringing AI to the edge creates unique challenges in latency, power, bandwidth, and security. To enable autonomous surgical robots, any time lag could literally mean the difference between life and death. AI for remote sensing platforms must operate within a tiny power envelope with limited connectivity. And maintaining data security is a challenging problem, even given large computational budgets. So doing so at the edge requires deep ingenuity. In scenarios where real-time decision-making is crucial, latency becomes a significant concern. Applications like hybrid human and robot manufacturing and autonomous vehicles cannot wait for data to be transferred to a central location for processing and then a response to be returned, even over the fastest wireless connections. Power consumption is another critical factor that limits the applicability of centralized AI to these edge applications. Remote healthcare monitoring and mobile devices need to sip energy rather than guzzling it like LLMs. As you can see, The GPUs powering most centralized AI applications are gluttonous consumers of power. As a point of reference, the amazing human brain operates on a parsimonious 12 to 20 watts. The hardware and AI algorithms running on edge devices must be optimized for low power consumption to ensure commercially viable battery life and reliable operation. Our current approaches to centralized AI requiring substantial power for data processing and transmission are simply not feasible in these edge situations. Bandwidth constraints at the edge also pose challenges for centralized AI. Applications like autonomous vehicles and augmented and virtual reality generate and leverage vast amounts of data for real-time processing. Transmitting this quantity of data to and from data centers for centralized processing is not efficient or even practically possible in many use cases. Edge AI, by processing the necessary data locally, can alleviate bandwidth limitations and enable faster, more reliable responses. Finally, security and privacy are paramount in sectors such as healthcare. Centralized AI systems require transmitting sensitive data to servers, increasing the attack surface of that data. Edge AI offers the potential for enhanced security and privacy by minimizing data transmission and reducing the exposure of sensitive information. Of course, we have all heard of the hacks that have been enabled by poor security at the edge, so we need to take edge security very seriously, including having the computing power and memory to run security agents at or close to the edge. Let's take a quick look at the regulatory landscape. As this slide indicates, governments are pursuing AI regulation around the globe, sparked by the astonishing growth and uptake of these large language models. We face a risk that, with the rapidly evolving nature of AI, legislation could end up being out of date even before it's passed and enacted. Also, the transition of AI to the edge, becoming more embedded in the very tapestry of our lives, requires us to do all we can to ensure the responsible use of AI, both within our own companies and collectively as an industry. These efforts will support our governments in creating the best possible regulatory frameworks. Now, as we explore AI for the edge, a myriad of applications opens to us. Start with mobility. Automotive is a very interesting and fertile proving ground for edge AI technology. On the one hand, there is enough power from the batteries or engine to perform medium-sized AI functions. But on the other hand, could we save weight and power and have a better travel and cabin experience with AI closer to the true edge? And where does the right balance lie, and how will this change and evolve over time? In automotive, road noise cancellation is not new. However, Edge AI has shown great promise in dynamically separating signal from noise in rapidly changing conditions and enabling the cancellation faster and more efficiently than ever before. This provides a better cabin experience for the driver and the passengers. Digital factory. In manufacturing, autonomous mobile robots can use Edge AI to learn and efficiently navigate complex dynamic environments, avoid collisions, and manage workflows. Hybrid manufacturing floors can leverage AI agents to monitor equipment, ensure workers' safety, and optimize production. Local processing reduces the latency and improves the reliability of these critical manufacturing operations. Edge AI is great in terms of using it for fault detection and handling on the factory floor, expanding the capabilities of condition-based monitoring and providing predictive maintenance solutions. The pattern recognition properties of AI make it uniquely suited for combining time series analysis, anomaly detection, and error handling. Smart infrastructure. Applications such as digital electric grids, building automation, traffic management, and public safety are also strong candidates for Edge AI. AI agents offer the ability to sense and optimize every node from electricity generation to transmission to consumption, and with the promise of achieving extreme energy efficiency and greater power supply reliability. Building automation systems can leverage AI to control HVAC, lighting, and security systems, enhancing energy efficiency and occupant comfort. Traffic management systems can use Edge AI to monitor the traffic flow and reduce congestion while simultaneously improving safety. Now, Edge AI is not just for new infrastructure. It can be used to better manage and control the systems in older buildings by retrofitting to make them greener and more efficient. Adding AI to existing digital building management systems will allow administrators to reduce energy consumption and manage dynamic bandwidth demands through real-time responsive action without extensive costs and remodeling. Finally, healthcare. Edge AI is already transforming healthcare by enabling remote patient monitoring, diagnosis, and treatment. Remote devices equipped with Edge AI can continuously monitor and analyze patient data to detect anomalies and provide only high-relevance alerts in real time to healthcare providers. Providing more and higher quality health monitoring in a home setting through Edge AI can not only keep healthy people out of the hospital, it can also detect developing health issues earlier, leading to better outcomes and quality of life for the patients. The applications of Edge AI are only limited by our imaginations. It can provide dynamic management of sound and speech acoustics in, for example, hearing aids and other applications in noisy environments. Edge AI can enhance network performance thanks to real-time signal management and improved data transmission efficiencies. And AI at the sensor edge could greatly streamline travel, security, and safety through the use of smart sensors and enable new forms of multi-factor authentication. If we put our collective heads together in this room, we could probably come up with, over an hour, over 100 great Edge AI use cases. But let's move to a new question. How to advance Edge AI? This is where the design elements come in. As I mentioned earlier, we need components, chiplets, processors, memory, interconnect, firmware, and software designed for AI, with AI, and by AI. Even if I simplify down to one binary dimension, generality, the solution is not obvious. Balancing the capabilities and issues of Edge AI with those of central larger-scale AI is critical at the platform and system levels to achieve optimal performance at minimal cost. So, where might we begin? Let's dig in a little more first to edge intelligence. Edge AI's more targeted applications trade breadth of knowledge for depth of knowledge. Here, domain expertise and knowing as much as possible about the application and its nuances becomes critical. At Analog Devices, we are not just known for our amazing analog and mixed signal processing. We are equally known for our deep experience and knowledge of these markets such as automotive, communications, industrial, and healthcare. We don't just hire hardware engineers, software programmers, and system engineers. We also hire biologists, mathematicians, chemists, and material scientists. We recognize that the future will belong to those organizations that can successfully combine exceptional technology solutions with deep domain expertise in highly targeted Edge AI applications. So, how does the Edge AI technology stack differ from the centralized AI stack? A centralized AI system consists of clusters of immensely powerful GPUs, CPUs, TPUs, ASICs. Did I leave anybody out? We'll keep going. Scalable storage of memory, robust operating systems, high bandwidth connectivity, and comprehensive software frameworks that support large-scale model training and inference. However, for the most valuable edge applications today, edge AI platforms need smaller, heterogeneous, and specialized technology stacks. These platforms integrate sensors, converters, smaller-scale real-time processing, lightweight operating systems, domain-optimized frameworks and libraries, model compression and optimization, and, of course, real-time processing. I should say a bit more about the hardware scaffolding supporting the signal chain at the edge. Modularity and chiplet-based designs have become popular in the digital world as a means of counteracting the slowdown of Moore's law. Heterogeneous integration technologies are even more critical when operating at the edge, where combining the full signal chain across heterogeneous CMOS or GAN or SiC on a single monolithic SoC simply won't work. By treating sensors, processors, and connectivity as modular components, manufacturers can customize AI systems and solutions to meet specific application requirements. Vertically integrating chiplets, eliminating the distance across a printed circuit board, squeezes even more latency out of the system. Now, I would be remiss in my duties if I didn't use this opportunity to call on all of the industry leaders here today to accelerate joint work on chiplet interoperability. Doing so will enable maximum flexibility in modular solutions, particularly around the inclusion of analog, mixed signal, and power technologies. Sensor inputs, ranging from cameras and microphones to environmental sensors, provide the raw data needed for processing. Just like we all learned in our introductory computing and engineering classes, garbage in, garbage out. The quality of the sensors and the data they capture determine the quality of the results of the system. Beyond individual sensor quality, edge AI systems will be fusing inputs from a variety of sensors to create a more comprehensive view and understanding of their environment. Sensor fusion will enhance the accuracy and reliability of AI predictions, but it can increase the complexity of a sensing system by an order of magnitude or more. Signal processing at the edge takes that sensor input and uses advanced processing techniques like filtering, noise reduction, analog to digital conversion, feature extraction, and data compression to prepare data locally for AI analysis. Moving beyond the signal chain, power management in edge AI is absolutely fundamental. For centralized AI, power management is essentially an economic concern. But at the edge, power management is an existential concern. Developing low-power AI algorithms and energy-efficient hardware for remote applications and to ensure long battery life and continuous operation is fundamental. Techniques that we use, such as dynamic voltage and frequency scaling, power gating, energy-aware scheduling, will all play a significant role in optimizing power consumption at the edge. Connectivity is another vital aspect of edge AI, where the need for real-time connectivity, both within the application and intermittent or at least unreliable connectivity to the cloud, must be managed and balanced. Efficient data transmission protocols and advanced networking technologies are necessary to manage the data movement both within and outside of applications. Now, not all data is equally important, so data management strategies within an application are necessary to streamline this communication. Techniques such as edge-to-cloud integration, adaptive bandwidth management, intelligent data routing can help optimize connectivity and ensure reliable communication outside of the application. Finally, as mentioned earlier, security is crucial in many edge AI applications, particularly in those sectors handling sensitive data. However, edge security is important across the board, both in maintaining the integrity of the data collected and the information generated, but also to avoid exposing connected systems to potential attacks. Robust security measures at both the hardware and software levels, such as hardware root of trust, TPMs or trusted platform modules, encryption, authentication, and access control, are critical. However, these must be designed intelligently for the smaller form factors and lighter processing at the edge. Memory and connectivity capabilities are limited, and so we must ensure that we have the power, the footprint, and the other things to do these. That is a very careful and difficult trade-off. Because we're here at DAC, let's talk a few minutes about the engineering enablement necessary to create these edge AI systems and how AI can, in turn, accelerate engineering. Product design used to be easier. Not that it was easy by any means, but it was less complex, and a solitary engineer or a small team was more the norm. Today, solutions require much larger teams to cover software, analog, and digital, and make them work together successfully. Now we're adding AI on top of these, and making all these systems work together is a huge challenge. And to be honest, simulation tools are struggling to scale to today's full products and deliver mechanical, thermal, and logic co-simulation capabilities that would allow teams to make the necessary trade-off decisions between software, packaging, and hardware that are needed to fully optimize system performance. Use of AI to optimize solutions and coordinate simulation with design, verification, and validation can be a major efficiency savings for our industry. But AI can do so much more than just simulation. It can help us develop the designs themselves. There are two primary AI-driven approaches to engineering enablement: analysis in the loop optimization through machine learning, and the process popularized by open source software of using generative AI and LLMs based on existing designs. Analysis in the loop optimization leverages AI in the design process in a test and refine model, enabling continuous improvement. By incorporating AI algorithms into design workflows, engineers can optimize designs in real time, identify potential issues earlier, and refine solutions. This approach enhances efficiency, reduces development time, and improves the overall design quality. Primary drawback of this approach is that it can only learn from whatever training an organization can give it and its own experience. The other approach uses generative AI and large language models incorporating existing designs to automate the creation of new designs and solutions. AI analysis of patterns in existing designs can extract insights and generate innovative solutions that meet specific requirements. Most of us are familiar with this approach in the software domain, where applications such as GitHub Copilot act as a virtual programming partner, suggesting entire lines or whole blocks of code. The drawback here, of course, is lack of availability of open source hardware information. But there may be ways for all of us to proceed together in some areas and with suitable initiatives from our EDA vendors. At Analog Devices, we always strive to be ahead of what's possible. In AI, this means understanding not just the edge, but the entire ecosystem. Recall our earlier Earth or world analogy. You had the core, the mantle, and the crust. We need centralized AI, edge AI, and everything in between. We need both to leverage their unique strengths and address diverse application requirements effectively. Centralized AI, hosted in powerful data centers with their high computational abilities and abundant resources, can best handle complex, large-scale data processing and model training. It facilitates collaboration and continuous updates, ensuring AI models are current and robust. However, edge AI provides real-time processing and immediate responses by operating locally on edge devices, reducing power, latency, and bandwidth usage, while potentially enhancing privacy and security by minimizing data transmission. Of course, as in the ball diagram, this is really more of a spectrum, and the combination of centralized and edge AI enables scalable, efficient, and versatile AI solutions across numerous use cases, from real-time applications to comprehensive data analysis. This hybrid approach, balancing across the spectrum, ensures that future technology solutions can meet the demands of different environments, providing both the depth of centralized processing and the immediacy of edge computing. Each use case needs to determine and drive the specific hybrid AI solution needed. Let's expand our aperture and consider some broad thematic areas for our technical investigations. Here you see 3 primary areas of discovery that form a top-down guide for future technology investments: health of human, health of planet, and autonomy. And let me address these with questions. Health of human. What if we could accelerate drug discovery, identify life-threatening diseases, and understand human biology at a faster, more cost-effective, and profoundly deeper level by leveraging semiconductor technology? Health of planet. What if we reimagined hydrogen as a platform, as one solution that could act as both an energy carrier and a converter to minimize CO2 emissions in hard-to-abate sectors? And autonomy and intelligence. What if we could develop the sensing and algorithmic processing capabilities to enable robots to be safely autonomous in human environments and dark factories without any human intervention whatsoever? There are a multitude of challenging areas of design interest for AI at the edge, and we could hold week-long conferences for most of them. Many of these week-long conferences actually exist. And we'd still only begin to scratch the surface. But here I'm just going to touch on 3 to conclude my talk: neuromorphic computing, federated learning, and responsible AI. One exciting field of research is neuromorphic computing, been around for a while, and it closely mimics the neural structure of the human brain to improve the efficiency and processing speed in artificial intelligence systems. With edge AI, we can extend this analogy to include the nervous system. As most of this audience is probably aware, this field is littered with many disappointments of promising ideas that seemed reasonable at the time, but just did not work out. I see at least 2 reasons for this. One is that we tend to conflate pattern matching at amazing speeds with the more esoteric branches of human intelligence. And 2, we often try to replicate our digital algorithms for said pattern matching in mixed signal or analog form, as opposed to contrasted with first principle analog modeling of these type of phenomena. As humans make progress in this area, we hope to achieve major breakthroughs in energy efficiency, real-time processing, and physical size of crust, mantle, and core systems. Much of this research is currently focused on the digital and centralized side of the house, but it is equally important to edge AI, where it can have impact on energy efficiency, real-time processing, and shrink the physical size of edge platforms. Again, we need to think of AI as one humongous system, the equivalent of the body's central and peripheral nervous systems. We should not limit neuromorphic computing simply to digital. Now, I certainly believe in extracting knowledge from the biological systems around us, but an important question I like to ask is this: why should we want or expect machines to think like we do as humans? Or more precisely, when and how do we want AI systems to think like us? And when and how do we want them to think in new and potentially more powerful ways? Federated learning, where the parts or periphery can learn independently and then contribute to the training of the whole or the core, has been around for some time, but it is far from seamless and efficient. Federated learning for AI trains machine learning models across multiple decentralized devices or servers holding local data samples without sharing those samples. Each device trains a model on its local data and then sends only the model updates, not the data, to that central server. The central server aggregates these updates to improve a shared global model, which is then sent back to the devices for another round of training. This iterative process enhances privacy and efficiency by keeping data localized and only sharing model parameters. In recent years, the AI community has made much progress in graph neural networks and related areas, but there is still so much work to be done. As we move forward on our design path to ever greater and more powerful AI technology, a word of caution. Let's take the time to think about the consequences of our actions. The leaders in this room, our colleagues, and our collaborators will be the ones to shape the future of technology for humanity. Responsible development of AI that is in turn responsible is critical for the future of humanity and our planet. As AI systems increasingly impact various aspects of society, responsible AI ensures that these technologies are developed and deployed ethically, transparently, and safely. It addresses issues like bias and privacy and accountability, preventing harm and fostering trust. By implementing ethical guidelines and robust governance, responsible AI can enhance fairness, reduce risks, and ensure that AI benefits all of humanity. This has been a very weighty slide, I understand that. And in closing, I thought it appropriate to quote from one of the great thinkers, someone from whom many of us learn to engage with the patterns and language all around us. That's right, Dr. Seuss. AI has already opened our eyes to a new world and opened our minds to new possibilities. Let's keep our hearts open on this AI journey to achieve great things for all humanity. There are many opportunities and challenges for all of us in AI, and it is going to take all of us working together to achieve its promise. We are still in the early days of AI, and no one company or even small group of companies can truly deliver its full potential. You, the leaders before me, will be the ones that shape our AI future. Thank you very much for your time, and I truly appreciate it. It's been an honor.